Hello, 535 people. This is Dr. Keith Schubert. We're going to be talking about eigenvalues and eigenvectors. So I just put eigen in here as kind of our reminder of what we're going to talk on. So let's start off with the basic kind of idea of this. And there's a lot of ways you can explain these, but I'm going to explain this from a kind of a computer sciencey sense of why we would want to find such a thing, and then we see if we can find them. Now, we've talked about complexity of multiplication and things of that sort. So let's say, for instance, I had a matrix A, and I want to multiply it by a vector x. Now, when we've done this, we've talked about the fact, let's say A is n by n, and our vector x is n by 1. So that's going to take a big O of n squared computation. All right, so we've got big O n squared. That's going on. Now, what if I could replace that big O of n squared operation by something that was, say, big O of n? That would be a tremendous improvement, yes? Well, in particular, what if I could say that I could do that by taking some scalar value, lambda, and multiplying it by x. That if as the result of that multiplication, I was just going to have to scale the vector. Now it would just be a scalar times each element, and that would just be big O of n flops that's going on. That would be a tremendous improvement if there was such a case or such a thing. All right, so that's one way we can look at why we would want this. It is a tremendous complexity improvement that's in here. Now, it turns out the only way such things will work, and they do indeed exist, every matrix actually has them, is, well, provided every square matrix has them, I should be very precise here, there is an extension of this into non-square, which is called singular values, which are wonderful things, and it does extend this, a slight variant to this theory, but a calculation of it anyway. But in any case, we can find these for the square matrices for which the definition would make sense, because in order for this to be the case, let me just show you why this has to be. If x is n by 1, a has to be something by n. And this is a scalar, so a scalar times a vector is just the vector, and this is n by 1. Well, the n times n, that's compatible, and what's outside has to end up being whatever this is, so that must be n. So the only way this definition makes any sense is if a is n by n, which is square. So let's take a look at how we can actually calculate these things and find them, because for square matrices they exist, they tell us an awful lot of things. They turn out to be amazingly important in a lot of physics equations that go on, and therefore are important for us computationally. So here we go. Eigen decompositions. Let's figure out how we can solve this. Well, we've seen so far that bringing everything to one side often does have some big advantages, because we can write things in terms of what we call those null space vectors. So we're going to pull this to the other side, and I've got ax minus lambda x has to equal 0. All right, so I'm actually looking for when something that is innately not 0, everything on this side isn't, happens to cancel out. That's what we mean by a null space. It ends up giving us null or 0. Now both of these involve x. Now in order to pull the x out of this one, there's got to be something left over that's the same size as this. So I have to do one of our famous math tricks. I multiply by 1, and the one you choose to multiply is very important. In this case, the correct one is the identity matrix, because identity times x is just x. It has not changed the equation at all. If I had chosen the scalar one, it wouldn't have helped me. But this identity has to be sized right for x, and that's got to be an n by n matrix. So now when I pull x out, I've got an n by n and an n by n, and the addition makes sense. So when I pull x out now, I get a minus lambda I times x must equal 0. And this is an n by n matrix, and that's an n by 1 vector, and everything's all good. That means this is an n by 1 vector also, just as a note there, an n by 1 vector of zeros. So we now have, this x, which is not 0, is multiplying something else and gives us 0. So this has to have something that's repeated. This cannot be a full rank matrix, otherwise this would not be possible. So we've found, in some sense, a characteristic value and a direction that tells us something about the matrix structure. Now we're going to break this down. Since this, therefore, has a 0 kind of in it, this is non-invertible. And there's things we can do to take a look at that. One of them is the determinant. Now we know a determinant of a matrix that is not invertible is equal to 0. Ultimately speaking, if the determinant equals 0, it does not have an inverse. Now this is kind of a result I am picking out of linear algebra, and I'm kind of presenting it to you and kind of whole cloth, because this is something that really would be a background area. You are welcome to look it up if you want, but I submit to you that you can accept this and look it up if you want, and it's at least still useful to you. This is a result you can calculate. Now, what can we do with this? Well, a determinant is actually fairly straightforward for a human being to calculate. It may be complicated, it may take a little work and all, but it is at least a straightforward calculation. And then we can solve for our lambdas. Now, eigen calculations doing this method is going to involve a lot of individual computations, which means the errors will build up horribly. So I will warn you in advance, this is a good technique for a human being. Once I say that, you should instantly distrust it for a computer. So if anybody attempts to solve a method using eigensystems and they use determinants, actually a determinant of anything, be very scared. It is computationally a horrible thing to do. But for human beings, we are not stuck with computers' problems, so therefore we can do some actual computation. Let's consider a matrix, and let's say we want to calculate these eigenvalues for a matrix. And let's say I pick A to be a really small, simple one. We'll do a couple quick examples here. I'll pick a really simple matrix. Now, in advance, if you look at and you have a matrix that is diagonal, the eigenvalues are just right on the diagonal. So the eigenvalues are 2 and 3 here. But we'll use this method to calculate it. And this is a good kind of sanity check because we can actually figure this out. Nice and simple on them. For instance, if my x was equal to 1, 0, and I multiply it times a times x is going to give me, well, 1, 0, that's times this will give me 2, and then 1, 0 times that gives me 0, and notice it's just twice, and that's one of the two eigenvalues. So this is the eigenvector associated with 2. Don't worry, I'll show you how to calculate these in a sec. I'm just showing you can actually see that these things do indeed work by calculating them out. The second x you should be able to guess is 0, 1 for this particular matrix, and that will give you 3 times that vector, which is exactly what we had said it would do. But before we get into that, that's just kind of a quick hint of why I picked this, because it gives me a quick, easy way to show you and for you to check. Let's stick it in and calculate this. Now, A is 2, 0, 0, 3. Well, it's a determinant, and lambda is an unknown value we're saying at the moment, and identity is 1, 0, 0, 1 in the 2 by 2 case, and we want that to be equal to 0. So what we get, lambda times here, just gives you lambda on the diagonals. So I just subtract element by element, and I get the determinant of 2 minus lambda, right, because it's 2 minus lambda, 0 minus 0, 0 minus 0, and 3 minus lambda. and that should equal 0. The determinant for the 2 by 2 case is this element times this element minus this one times that one. So what I end up with is 2 minus lambda times 3 minus lambda, and that has to equal 0. Now if you distribute this, you get 6 minus 5 lambda plus lambda squared equals 0. This is now a quadratic formula, and you can stick it inside of everybody's favorite little quadratic. So we just say lambda equals minus b, so that's 5, plus or minus the square root of b squared, 25, minus 4 times ac. So that's 4 times 1 times 6 is 24, all over 2 times a, which is 2. So that's 5 plus or minus 25 minus 24 is 1. Square root of 1 is 1, all over 2. So 5 plus 1 is 6, divided by 2 is 3. 5 minus 1 is 4, divided by 2 is 2. So you get the 2 and 3 that I mentioned. Okay? So easy enough to calculate on those. Alright, so there is a first example of what we can do. Now, I would like to show, I just erase the upper determinant. Well, you can rewind the film if you want to. Now, there's kind of a funny statement. Rewind the film. I should actually kind of laugh at myself. I'm dating myself, talking about this is a digital movie. There's not a single piece of film inside this camera, and yet I call it film. That's kind of funny. Now, let's say we slightly perturb this, and I ended up with a matrix that looks like this. A small perturbation, you expect it somewhat close by. In fact, it really does actually follow it quite nicely. But this will give us a fun thing to calculate off. And we'll just do the eigenvalues, and then we'll go back and do each of the eigenvectors. So let's consider this one. So now I've got 2, 1, 2, 3 minus lambda times I, we've already shown, just puts lambdas on the diagonal. And that must equal 0. So when I'm doing this, I just subtract lambdas on the diagonal. 2 minus lambda, 2, 1, 3 minus lambda. Once you get used to this, you'll just start taking your matrix and just doing minus lambdas on the diagonal. It makes your life a lot easier and quicker. So that has to equal 0. And now we do the determinant. This one times this one minus that times that. So I get 2 minus lambda times 3 minus lambda, and then minus 2 equals 0, which gives me 6 minus 5 lambda plus lambda squared minus 2 equals 0, which is 4 minus 5 lambda plus lambda squared equals 0. Again, quadratic formula. 2 by 2 matrix gives you quadratic, 3 by 3 you get cubic, so on and so forth. So in any case, we take this and we stick it in our formula, so we get that lambda has to be equal to minus b, which is 5, plus or minus the square root of b squared, which is 25, minus 4ac, which is 4 times 4 times 1, which is 16, all over 2a, which gives me 2. So 25 minus 16 is 9, square root is 3, almost like I pre-thought about this. Oh wait, I did. I fully admit I picked my numbers to make my life easy as this goes. Not only that, I even picked it so that I would get an even number up top so it divided nicely, because that makes my life easier. 5 minus 3 is 2, 2 divided by 2 is 1, and then 5 plus 3 is 8, divided by 2 is 4. So you get 1 and 4. So they've just kind of moved out away from each other. Remember there were 2, 3 before. now they are 1, 4. This will become kind of fun when we talk about a little bit later Gershgorin disks and things of that sort, but I'm not going to go into Gershgorin theory right now. Okay. So, we have calculated eigenvalues for 2 different matrices. So, we found that for 2, 3 with zeros, we had 2 and 3. And for 2, 1, 2, 3, we had 1 and 4. Now let's find the eigenvectors. Now the eigenvectors are the x's that are associated with these scales. So what you do for these, if you remember, we had that a minus lambda I times x had to equal 0. So this gives us a nice little formula, but now we know what the lambdas are, so we can stick it in. This becomes a completely known matrix. So now x is solvable. So let's take this one first. We already know this just puts the minus lambdas on the diagonal, so we do it for the first one. We say lambda equals 2 and put it in. Well, that gives us 2, 0, 0, 3 minus, and it's 2's on the diagonal, that whole thing times x. Well, x has to be a 2 by 2, x1, x2 has to equal 0 as a vector. 2 minus 2 is 0. 0 minus 0 is 0. 0 minus 0 is 0. And 3 minus 2 is 1. So this is a minus lambda I times x1, x2 equals 0, 0. The first equation gives me nothing equals nothing. That's this row. Tells me 0 equals 0. And the second row tells me x1 times 0 plus x2 times 1. So x2 equals 0. So that means x2 must be 0, but x1 can be any number you want. Now we normally normalize this, which means we would pick x1 to be 1, because that would give it unit length. But realize you're not required. Actually, anything in that direction. It is literally a direction, so any vector in that direction will work. So we have discovered that associated to lambda equals 2 is vectors that are scalar multiples of that. Now, if we now try to calculate the other one, lambda equals 3. Hopefully you guys are getting comfortable with this idea of it's going to affect the diagonal elements. So when I subtract 3 from each of the diagonal elements, 2 minus 3 gives you minus 1, and 3 minus 3 gives me 0. This is what a minus lambda I has to be when lambda equals 3. And then this multiplies x1, x2, and that has to equal 0. The first row tells me minus x1 plus nothing equals 0. And the second one tells me nothing equals nothing because it's 2 zeros. So this one right here tells me that the first element must equal 0. Normalizing the second element, we make it 1. So we have discovered that the associated eigenvalues for this matrix are just your standard kind of x and y direction. How about for this lovely thing? Well, a is now slightly different, and we're going to subtract 1. So a looks like 2, 1, 2, 3. And then from the diagonal elements, we subtract 1 first. So this is lambda equals 1. Lambda equals 1. From the first element, we subtract 1. From the second diagonal element, we also subtract 1. So you get what you notice, even though there's no zeros in here, notice this column and this column are identical, or you could think, right, because they're just multiples of each other. So they're dependent on each other. this row and this row are identical, so therefore they are exact copies of each other. So whenever you see dependent vectors, you realize one of them's unnecessary. There's a kind of an old joke. When there's two people and they're exactly the same, one is unnecessary. Alright, so x1, x2 equals 0. Okay, so from the first and second equation, they're identical. So therefore I only need to calculate one of them, which I get x1 times 1, x1, plus 2 times x2 has to equal 0. So that tells us that what we usually do at this point is we pick one, and we just say, hey look, let x1, right, or actually in this case I'm going to pick x2 equals 1. The reason why I'm going to do that is because it's just less work. So less work is good in my land. If x2 equals 1, right, because you could pick it, because I'm just going to normalize it, right? So you're never going to guess the normalized value, but who cares? I get a vector in the right direction, and then you can just divide by the length, and now you've got a normalized one. So I just pick this one in 1, so that because I multiply here, 2 times 1 gives me 2. So x1 plus 2 has to be 0, so x1 has to be minus 2. So I easily get the direction. I can just stick here that this has to be minus 2, 1. And then if you want to normalize it, all you have to do for normalization, you square the first, you square the second, add them together. So that's 4 plus 1 is 5. So this is length square root of 5. So all I have to do is divide by length square root of 5. And now I have a normalized vector in the right direction. Okay. Let's do the same thing, except now lambda equals 4. So we start off 2, 1, 2, 3. And then we take minus 4 to the diagonal elements. That's minus 4i. 2 minus 4 is minus 2. 3 minus 4 is minus 1. And you'll notice that if I take this row and multiply it by minus a half, I get this row. Or you could think if I take this column and multiply by minus 1, I get this column. So again, they are multiples of each other. They must be multiples of each other. So if that does not happen, they are not dependent on each other, then you didn't have an eigenvalue. Alright, so they are dependent. That's awesome. And this has to equal 0. That means really only one of these equations will do anything for me. Just like before, I had a 0 equals 0. Then I had an equation that did something. Well, here I'm going to get two equations that do the same thing. So since they do the exact same thing, I'm going to pick the bottom one, because it's just a simpler equation, which is x1 minus x2 has to equal 0. Yeah, so taking minus 2x1 or plus 2x2 is exactly the same thing. Take it to the other side, divide by a half, and you're here. So there is no difference between the two that you would get, whether you do the first row or the second. This means x1 must equal x2. Right? Take it to the other side, x1 equals x2. That means this has to look something like 1, 1, but that's not unit length. Alright, so this is actually length square root of 2, so 1 over square root of 2. And how did I know 1, 1 was length square root of 2? Well, 1 squared plus 1 squared is 2, square root. There you go, square root of 2. So now we've got each of these. If you want to draw them, and as we showed before, this one right here has 1, 0 points in the x direction and 0, 1 points in the y direction. When we get to this one, it's minus 2 in the x direction. So you kind of consider your space. You go minus 1, 2, and then 1 in the y. So that's the first. This is the lambda equals 1. and multiples of that one just define this entire line. This one is 1, 1. Now notice these are not 90 degrees off from each other. These ones were. So you don't always get that they are 90 degrees. In fact, this is bigger than 90 degrees and that's less than 90 degrees. But there is life. So that's this one. This is lambda equals 4. And it turns out that you will get on this based on the eigenvalues. If you plot out, you will get an ellipse. Now, it's kind of natural to ask, what do I mean by plotting out and getting an ellipse? Let me first off do it for this one. Okay? What we do is we consider, what if I had the vector x that was multiplying it? What if I did x transpose, and then we did a x? Well, in this case, x is x1, x2. But I'm going to call it, instead of x1, x2, I'm going to call it x and y, little x and little y. There's the transpose. A is 2, 0, 0, 3, and x is xy. I'm just doing that because in the end that xy will give you what everybody else thinks of the coordinates. So first I do this multiply, x times 2, y times 0. I get 2x. And then x times 0, y times 3, I get 3y. That's the result of this. This multiplies that, so I get 2x times x. And then I get 3y times y. And that has to equal whatever we want as our, some type of value as it goes on. But that's our basic equation. If you think about this, this is the equation of an ellipse. Okay, and this is an ellipse that is set on the xy axis as major and minor, and you can go through and just plot the points of that, let that equal 1 or something and plot the points. As it goes around, this right here, you can kind of consider this as, 1 over the radius in that direction, 1 over radius in the other. Anyway, that's why we call them ellipses, and then these become your axes, and the eigenvalues now relate to, in some sense, how large you are in that direction, and this is 1 over the ellipse's radius. So same thing applies here, except these are now non-orthogonal, so you just kind of have a tweaked ellipse. An ellipse that's been kind of stretched in space in a weird way as it goes. Anyway, that's what we mean by an ellipse for it. So these are things we can, if you want, do it. I'll leave this one for you to try out. If you have any problems trying to plot it out, then, or get what it looks like and why it's an ellipse, and we can talk about that one in class. Or you guys can ask me to record another video for you, and I'm happy to do that. So hopefully this gives you a good idea or a basic introduction into eigenvalues. Rewind, try it over, do some numbers, and hopefully you'll feel better, and then we'll go over this in class. Have a good weekend. Bye.